In 8.3, we're going to talk about the trigonometric integrals. So this is a type of integral that involves a lot of techniques. Especially, we're going to use substitution quite a bit for trigonometric integrals. Trigonometric integrals essentially means, in the integrand, you have trig functions, and usually it takes a lot of effort to do the integral. And the fact is, we cannot do all of the trig integrals, even a lot of them. What it means is we may end up with the situation that we cannot find the analytical expression for integration, and then we have to seek for a numerical solution for those kinds of integrals. But there are still a few types of trig integrals that we can figure out. We have summarized several cases, several categories that we can actually find, analytical integral for these integrals. And we're going to start from, the integrals involving powers of sine and cosine functions. All right. And then we discuss, integrals involving tangent and the secant functions. And in each category, we have several cases. All right. Okay, the first case in the first category. So when the integral involves powers of sine and cosine functions, the first case is the power of sine is odd and positive. Okay, so we're talking about a product of sine and cosine functions with the power of sine function is odd and positive. In this case, we use substitution u equals cosine x, and we don't have to worry about the power of cosine function. Okay, so let's see one example and we'll explain the, why that's the case. So in the first example, we want to carry out the integration of sine x cubed times cosine x fourth. So in here, the power of sine is odd, is 3 and positive. Okay, so 3 is greater than 0. So according to the rule, we're going to use substitution u equal to cosine x. So to carry out the integration by substitution, we need to find out du, which is differential of u is defined as derivative of u times dx. So the derivative of cosine x is negative sine x. So du is negative sine x dx. If you divide by negative sine x on both sides, you get dx equals negative du over sine x. And then you just use the trig identity sine x squared plus cosine x squared equal to 1 to rewrite sine x squared as 1 minus cosine x squared. Okay. Then we can, plug in dx and using this formula to replace everything in the original integral. So then what do we get? Is sine x cubed times cosine x to the fourth times negative du over sine x. If you replace dx by negative du over sine x as we got. And you can cancel one sine x inside the integrand and pull out the negative sign. So that becomes negative integral sine x squared cosine x to the fourth. And then replace 1 minus cosine x squared for sine x squared. We got a 1 minus cosine x squared times cosine x to the fourth. And then just distribute cosine x fourth. We got cosine x fourth minus cosine x to the sixth inside the integral. Now, just replace cosine x by u as we, defined. So the whole thing just becomes negative integral u to the fourth minus u to the sixth du. And then we can just integrate easily using the power rule for u. So we got to use the 5 over 5. Remember, you just add 1 in the exponent and divide by the same number when you integrate the power function. So that's the first term, and the next, the other term will be minus u to the 7 over 7 using the same rule. And then just plus c. So that's the result, but we need to replace u by cosine x. And you can also distribute the negative sign in the first term to get cosine x to 7 over 7 minus cosine x to 5 over 5 plus c. So that will be the final answer because you start from the trig function with variable x. So you need to write the final results in x. So does it make sense to you? Any questions for this example? Good. Okay, so that's the first case. The power of sine is odd and positive. Now the other case is obviously the power of cosine is odd and positive. Then we're going to use substitution u to equal sine x, just in a symmetric with case 1. So that will be case 2, and I guess I will not explain and discuss any examples. So power of cosine is odd and positive. Use substitution equal to sine x, case 2. Now, this covers the powers of sine or cosine odd and positive. But what happens if the power of sine or cosine is even and non-negative? Okay, then we have to use the double angle identity. Okay, so for example, if you want to integrate cosine x to the fourth, and then we can use the double angle identity cosine x squared equal to 1 plus cosine 2x over 2. And this double angle identity is valid for any angle x. So especially when you replace x by 2x in this formula itself, it becomes cosine 2x squared equals, because cosine 2x squared equals 1 plus cosine 2 times 2x plus 2. 2 times 2x is 4x. So we got this identity cosine 2x squared equal to 1 plus cosine 4x over 2. So that will be used in this particular problem. So what do? We just rewrite cosine x to the fourth by using the double angle identities and lower down the powers. Okay. So the first step is to rewrite cosine x to the fourth as cosine x squared to the square, right? If you multiply 2 by 2, you get 4. So they are equal. And then cosine x squared, we know is 1 plus cosine 2x over 2. So just you write that in here, and then you square it. Okay. Now you have to FOIL the whole thing. So if you multiply 1 plus cosine 2x over 2 by itself, you're going to get the 4. in the denominator, 2 by 2 is 4, and then you multiply 1 plus cosine 2x by itself, you FOIL it. You're going to get 1 plus 2 times cosine 2x plus cosine 2x squared. Remember, a plus b squared. If you FOIL it, you get a squared plus 2ab plus b squared. Okay. So then we got the cosine 2x squared that can be, replaced by 1 plus cosine 4x over 2 in here. That's why we need the other double angle identity. So then we can, combine like terms on the top and do a little simplification. So, for example, you can combine 1 plus 1/2. Okay, you get 3/2. So then, on the top we just have 3/2 plus 2 times cosine 2x plus cosine 4x over 2. Okay, if you break up 1 plus cosine 4x over 2 as 1/2 plus cosine 4x over 2. Okay, and the whole thing divided by 4, you just divide by 4 for each term. So you're going to get 3/8 from 3/2 and 2 over 4 in the second term, which reduces 1/2. So that's 1/2 times cosine 2x, and the last term is just cosine 4x over 8, right? So if you don't know how to do fractions, you can just multiply 1/4 on each term on the numerator. What you get is this. Good. Any questions? So just be careful about the fractions. Don't try to mess up. Any questions? Okay, so then that's the cosine x to the fourth we start. So we just replace cosine x to the fourth by this and the integrate term by term. Now everything is just in the first power of cosine of a constant, then can be easily integrated. Okay, and that's the whole point of using the double angle identity. You just lower the power when you use the identity. So let's just finish this problem. So I just rewrite cosine x to the fourth as 3x plus 1/2 cosine 2x plus cosine 4x over 8 as we got in the last step. And then you just integrate term by term. So we get 3x plus 1/2 times the integral of cosine x, which is sine 2x over 2. I will explain how to do that. And then the last term is 1/8 times the integral of cosine 4x, which is sine 4x over 4, and plus c. So just simplify the terms. You get 3x sine 2x over 4, 2 by 2 is 4, and sine 4x over 32, 8 times 4 is 32 plus c. Okay, so when you integrate cosine 2x or cosine 4x, you use substitution for u equal to 2x or 4x in those cases. So just follow the same procedure for substitution. Take a differential of u, get du equals 2 times dx. Take a derivative of 2x, you get 2, and then times dx. So if you divide by 2 on both sides, that becomes du over 2. So dx is just du over 2. Now, the integral cosine 2x, it just becomes cosine u times du over 2. 2x is u, and the dx is du over 2. So now just integrate over u, you get a sine, if you integrate cosine, you get a sine u, and you get the 2 in the denominator. and plus c. So at the end, I replace u by 2x. All right. So that's sine 2x over 2 plus c. So that's why you get the factor of 2 in the denominator. And similarly, if you integrate cosine 4x, you're going to get the sine 4x over 4 plus c for the same reason. Any questions? So good. All right. So that's the integrals involving powers of sine and cosines. Okay. So the second category, talk about integrals involve powers and powers of cosine and tangent. Okay. And we still have different cases in this category. Case 1 is the power of tangent is odd and positive. Okay. The power of tangent is odd and positive. Use substitution u equal to secant x. All right. And these are the rules, people summarized from, a lot of examples. There, of course, there are reasons why that works, but at this point, you just follow the rules. You're going to see, how you can proceed with that technique. So, for example, we want to integrate tangent x cubed over secant x squared, square root of secant x. So in this integral, it only has tangent x and the secant x, powers of both functions. And the power of tangent is odd, is 3 and positive. 3 is greater than 0. And you don't have to worry about the power of secant x. So according to the rule, we're going to use substitution u equal to secant x. So let u equal to secant x. You do the differential for u. So what you do, just take the derivative of x for secant x and times dx. And that will be secant x tangent x dx if you check the table for differentiation. So if you divide by secant x tangent x on both sides, you get dx equals du over secant x tangent x. Now, we also need another identity, a trig identity here. Secant x squared is 1 plus equals 1 plus tangent x squared. And to rewrite the tangent x squared as secant x squared minus 1 if you subtract 1 on both sides. Now we can carry out the integral to replace dx by du over secant x tangent x. And you can also rewrite square root of secant x as secant x to the half in the denominator. Okay, so then we can do some cancellation and combine secant x. So tangent x cubed cancel one factor of tangent x, so becomes tangent x squared on the top and the secant x to the half and times secant x. So secant x is just secant x to the 1th power. So when you multiply secant x to the half times secant x to the 1st power, you just add exponents 1/2 plus 1. That would be 3/2. Okay. Now you can use the identity tangent x squared equals secant x squared minus 1. So then you divide by secant x 3/2. So what you do, you just break up into 2 fractions. So that becomes secant x squared over secant x to 3/2 minus 1 over secant x to 3/2. Okay, so in the first term, you just subtract the exponents. You divide the 2 powers of secant x. So 2 minus 3/2, you just get 1/2 if you rewrite 2 as 4 over 2, right? And the second term is just the secant x to the negative 3/2. It's in the denominator. So you just use negative exponent. Now you can rewrite secant x as u, as we defined earlier. So the whole thing just u to the half minus u to the negative 3 halves. And we can easily integrate the function by using the power rule for each term. So just add the exponent by 1 and divide that number in each term. So we get u to the half plus 1 over half plus 1 minus u to the negative 3 halves plus 1 over negative 3 halves plus 1 plus c. So again, half plus 1 is just 3 halves, and when you divide by 3 halves, you flip it, you get 2/3 in the front. So the first term is 2/3 u to 3 halves, and the second term, negative 3 halves plus 1, you write 1 as 2/2, so that becomes negative half. So we get u to negative half on the top, and then divide by negative half. And then, in the second term, we got 2 negatives. So that becomes positive, and you can also flip the 1/2 to get it 2/1 or just 2. So the second term is 2 times u to the negative half. Now replace u by secant x. So the final answer is just 2/3 times secant x to the 3 halves plus 2 times secant x to the negative half plus c. So that's the final answer for this example. Any questions? So again, we just use substitution and proceed with the standard steps. It's not especially difficult if you do it step by step. Any questions about this example? If not, then we go to the next page. Okay. So that's the case 1. Power of tangent is odd and positive. So we have another case, the second case, when the power of secant is even and positive, you use substitution u equal to tangent x. So that's a different case. And we have another case 3. Power of tangent is even. Use substitution u equals tangent x also. So case 2 and case 3, they're very similar. You can do the problems in the same way as we did as in case 1. Case 1 is power of tangent is odd and positive. Now we're talking about, power of secant is even and positive, or power of tangent is even. So in those cases, you use substitution u equal to tangent x. And I'm not going to explain to do any example. Well, for this case, they are very parallel. The procedure is always the same, do substitution. And the other case, converting to sines and cosines. So it is always helpful when you have different trig functions to integrate, you convert all those functions in terms of sine and cosines. And then we can use the rules for the first category to perform the integral. And that's always a good approach. Okay, so case 4. So let's just do one example by using this approach. We're not going to repeat the procedure or examples for case 2 and case 3. They're just parallel to case 1. So in this example, we need to integrate the secant x over tangent x squared. So instead of dealing with secant and tangent functions, why don't we just rewrite secant x and tangent x by using the reciprocal relation and quotient relation. Okay, so secant x is just 1 over cosine x, if you remember, and tangent x is just sine x over cosine x. Okay, so now just rewrite the whole thing by sine and cosine functions. So we got 1 over cosine x on the top and sine x over cosine x squared at the bottom. So when you divide a fraction, it's flip it. So the integrand is just 1 over cosine x times cosine x over sine x squared. Okay, when you flip sine x over cosine in the denominator. And now you can cancel one of the cosine x from the bottom, and you just left with the cosine x on the top. Okay. And then you get sine x squared at the bottom. So if you use the rules we just did for first category, when the power of cosine is odd than the positive, you use the substitution, you equal to sine x. Okay. So take a differential of you get cosine x dx. The derivative sine x, just cosine x. Now the integral cosine x dx or cosine x sine x over sine x squared dx. You can replace cosine x dx by du, and the sine x squared is just u squared. U is just sine x. So you just integrate 1 over u squared basically, and that's easy to do if you write 1 over u squared as u to the negative 2. So using the power rule, you get u to the negative 2 plus 1 over negative 2 plus 1 plus c, and the negative 2 plus 1 is just negative 1. So we got them u to the negative 1 and the negative 1 in the denominator, which brings up a negative 1 for the whole thing. So the answer is negative u to the negative 1 plus c. If you replace u by sine x, you get them negative sine x to the negative 1 plus c. So that's the final answer. Any questions for this example? So this one is very straightforward, I think, compared to the examples we just did there, previously. Okay, so there's another category that we need to pay some attention to. So we just separate this case from the trig integrals. That is the integrals involving sine cosine products with different angles. Okay, so all of the examples or cases we discussed before were trig functions with the same angle. So what happens if the sine and cosine functions have different angles, and if you got this kind of products, how do you integrate? In this case, we're going to use the trig identity from product to sum. So this is another property or identity for trig functions. The identity is sine mx cosine nx is equal to 1/2 times sine mx plus nx plus sine mx minus nx. So we have a lot of trig identities. So that's another one. So then we can rewrite this sine cosine products with different angles into a sum of two sine functions for this particular example. Okay. So the example here is to integrate sine 5x times cosine 4x. So if you let m equals 5 and n equal to 4, then we get the sine 5x cosine 4x equals half sine 5x plus 4x plus sine 5x minus 4x. Okay. And 5x plus 4x just 9x, and 5x minus 4x just sine just x. So the integrand, the function to integrate, is just 1/2 times sine 9x plus sine x, which is very easy to integrate. So so you just integrate this by using substitution for sine 9x. So taking out 1/2 from integrand. And when you integrate sine 9x, you get negative cosine 9x over 9. We discussed that before today. Using substitution, u equal to 9x, if you still remember. Okay. And the sine x just give you negative cosine x when you integrate it. And so then plus c. So at the end, you just distribute 1/2 into the two terms in the first part to get negative cosine 9x over 18 minus cosine x over 2 plus c. So 2 times 9 is 18. All right. So this just give you a reminder, how do you integrate sine 9x? So we already did that before, but they just remind you how to do it. Again, use substitution u equals 9x. And then take a differential of u, you get the du equals 9 dx. The derivative of 9x is just 9, but you still need to multiply dx to get the differential. Okay. And divide by 9 on both sides, we get 9. We got dx equals du over 9. So just replace 9x by u and dx by du over 9. Okay. So we got sine u du over 9. So basically, just integrate sine u, you get negative cosine u, and then you divide by 9 and plus c. So u is just 9x. So that's just equal to negative cosine 9x over 9 plus c. So that's the section 8.3. Some trig integrals, some techniques we can use to carry out trigonometric integrals. Any questions about this example? Any questions about this whole section?